Hi, I'm Ben-Yaakov. This presentation is entitled Current Sensing by Hall Effect. Let me just note that the companies and product mentioned and described in this tutorial are shown just for educational purposes only. There is no endorsement or recommendation implied here. The Hall effect was discovered by Edwin Herbert Hall in 1879, so it is known for many years now. But at the early years, it was not used that much. One of the reasons, because it takes quite a bit of sophisticated electronic to make it go. For example, the output voltage is very low, so you have to have good amplifiers, low offset voltages, etc. And only with the emerging of the microelectronics technology, the use of the Hall effect became more and more practical. So today, Hall effect devices are used in many applications. I'm just showing this aspect of current sensing. Now, the basic concept of the Hall effect is based on the fact that when you have a current flowing through a conductor, this is a conductor, here's the current, and it is shown as the charge carriers are, say, electrons. And if there is a magnetic field, and of course there's a force on this path, on this current flow, and therefore there'll be accumulation of electron in this side and a lack of electron in this side when there is a current, of course, passing through the device. Consequently, you'll have a potential difference here being negative and here positive, and this is the Hall effect. And this is the voltage as you measure, which is a function of the magnetic flux going through this device. So this is the very basic concept. And of course, there are materials which have higher Hall effect constant, that is, for a given flux and current, they'll generate a higher voltage. But in all cases, we are talking about a very low voltage in the millivolt and sometimes in the sub-millivolt range. Now, modern devices are built in microelectronics by microelectronics technology, and here Allegro shows, say, a cross section. We see here this is the conductor, and here we have the bias. This is the current passing from here to ground, and then we have the, say, magnetic flux going here, and the measurement of this, the output will be between these 2 points. So this is a small device which is constructed or manufactured by microelectronics technology. Now let's see what's the basic physics behind it. We have Ampere's law, HDL is n to 1, the circular integration. In this case, if we have one wire with a current at n is equal to 1, the length here for a given radius is 2 pi r. B is mu, total mu times 8. This is mu relative permeability times vacuum permeability, when the vacuum permeability is expressed like this in SI units. Now, let's take an example. If we have a radius of 1.5 millimeter, the path here, the circle will be 2 pi, this value, which is about 1 centimeter. Assume a 1 amp current. H will be 1 over 10 to the minus 2, or 100 ampere meter. B is then mu 0 times, this is air here, times 100, which comes up to be 1.2 10 to the minus 4 Tesla. Now, 1 Tesla is 10 to the 4 Gauss, so therefore we're talking about 1.2 Gauss. This will be for a distance of about 1.5 millimeter from a wire conducting 1 amp. And to get it in proportion, the Earth magnetic field is about 0.5 Gauss, okay? 0.5 10 to the minus 4 Tesla. So the 1 amp, and we are pretty close to it, gives us 1.2 Tesla 10 to the minus 4 Tesla, and here we have 0.5, so we are pretty close. So for low current, it could be a problem. As the current goes up, of course, the magnetic field will be stronger and stronger. But again, we're talking about small signals, and there's a problem, of course, of interference from first of all, the magnetic field of Earth, and then if you have some circuits, magnetic element, inductor, transformer, etc. around it, there might be a problem measuring here the magnetic field in order to get a measure of the current. Now, current sensing by Hall effect is done today in basically two ways. One is the non-intrusive, and that is indeed you put a Hall effect device one way or the other. This is conceptually here, close to the wire or around it. And here we have the invasive method in which you are passing the current through the device. Now obviously, if the currents are very heavy, say hundreds of amps or maybe more, this would be very difficult to pass the current through a device because of the heavy wires involved. So for very high current, usually the non-intrusive approach is taken. Now, let me start with this then method, non-intrusive or direct. In this case, we have a Hall effect element which is nearby a conductor. Now, as I've said, there are problems of interference from around the element. If it is a switch mode converter, we might have switching element, and transformer, inductors, all with magnetic field around them, and this of course will interfere here. There is also a sensitivity problem, as I've said, that the magnetic field you get, especially for low current, is very small. Having said that, let me just mention that the trend now is to go to this approach. Just put the bare element outside the, say, a bus bar. It's shown here is a PCB and a bus bar, and there is a sensing element. This is not a Hall effect element. This is a tunnel magnetoresistance element made by Micro NAS. It's a subsidiary of TDK. It's a different technology, but the point is that the direction now is toward this approach, and there's some example of systems like this with a Hall effect, but in the majority it is not. The Hall effect devices are not used this way. This is just putting them adjacent to the bus bar, but rather using the so-called concentrator. Well, a concentrator is in effect a ferromagnetic material, a ring or any other shape, in which has a slot or a gap, and you put the sensor, the Hall effect sensor, within the gap. Here with the cross section, we have here the ring, in this case, a toroid with a gap, and the magnetic element is put here. This is the conductor, and this is the current. So this is the most common way of using the Hall effect in the case of the non-intrusive method. So let's have a look a little bit again at the physics of this situation. We have a path here, which is now ferromagnetic, which has a high permeability, and I define here two lengths here. One is the gap length, Lg, and one of the lengths of this ferromagnetic material. Okay, it's L sub F. Now again, Ampere's law. In the case of no element like this, no concentrators, of course we're going to get I over the total length. Okay, I over the length. This will be the magnetic field. However, in this case, we have to break this circular integral into two parts. One is Hg, the magnetic field within the gap times the length of the gap, and the magnetic field within the ferromagnetic material times the path, the length here, Lf. These two are not equal, and that's the whole point. Now B is mu, total mu times H, and B now is constant. That is, we have the same flux magnetic flux throughout this system, including both the ferromagnetic element and the gap. Save some fringing here that you might have some of the flux lines coming out. I'm just assuming that the gap is small enough, so you basically have the same density, flux density within the gap. So since B's are constant, then we can say that mu 0 times Hg is mu r mu 0 times Hf. This is within this magnetic filament, and I can then therefore express the magnetic field here, H sub f, as a function of the magnetic field here. Just from here I get this thing, which shows that the magnetic field within this ferromagnetic media is smaller by mu sub r from the magnetic field within the gap, or what is more important, the magnetic field within the gap is larger than here by mu r. Mu r for ferromagnetic material in the thousands or 3,000, 4,000, or even higher, like some materials would have 10,000 values, so this is a large number. So now we have this actually Ampere's law written this way. This is the sum of the two. Now I'm replacing this by the magnetic field within the gap, and I'm getting this expression now, and from which, just to check, if mu r is 1, I'm getting back what we had before. But in our case, when mu r is not 1, and from here I get expression for the magnetic field within the gap, and if this number, the length of the gap, is larger than Lf over mu r, or Lf mu r is much smaller than this, we end up with this expression. This is the expression. The magnetic field within the gap is the current over the length of the gap. And this will hold, of course, if mu r is large, because with a large number this becomes small and we can neglect it. Or we can say that we want mu r to be larger than the length of the path in the ferromagnetic element over the gap. And this usually will be the case because, as I've already said, this could be thousands, and here we might have like 10, 100 at most. So this holds, and therefore this is what we're getting. Now recall that the magnetic field that we found without the concentrator, here it is I over the total length. And here we have only this one. Now this one is much smaller, like 10 times or 100 times. So therefore the magnetic field within the gap is much higher. And that's the whole point. That's the point of this so-called concentrator, of concentrating and making the magnetic field much larger here in the gap than here, sort of concentrating all the magnetic field here. And this is because the mu r is here high, B is the same, and therefore H here is much lower than H here. Let's take an example. Suppose we have a length of the ferromagnetic material of 3 centimeter, a gap of 3 millimeter. That's pretty large, could be 2 millimeter, but let's assume 3 millimeters, so the ratio is 10. Let's assume mu r is 3000. So here we have the approximate solution, and it is 10 times in this case, because this is 3 centimeter, this is 3 millimeter, 10 times what you would get without a concentrator. That's quite a bit. And in this case, we're going to have B will be equal to mu 0, this is in the gap, times this magnetic field value, times current, and it comes up to 3 to 10 to the minus 4 times the current Tesla, or 3 times the current Gauss. So this is the function of this concentrator to increase the magnetic field in the area or in the volume where the Hall effect is there. Now in practice, this is how this is done. We have a set of toroid. It may not be a toroid, it could be a square, it could be any other shape. We have a gap, and we put this element, Hall effect element, inside this gap in order to capture the magnetic field here. Now, shown here, this is just the same thing. Here we have a housing just for protection, and we have the element here inside. Now, shown here is a laminated core, you might say, that is made of sheets of steel which are separated here. This is to avoid eddy current. I'll talk about it later on. So, just to get an impression of what are the elements available today, I'm just going to look at the data sheet of one element, one device from Allegro. So let's go and look at it. So here's the device. It's a A1363. It's described as a low noise, high precision, programmable linear Hall effect sensor. Linear means that the output is linear, the output voltage is linear with the magnetic field sensed, and it has temperature compensation and a high bandwidth of 120 kilohertz. So this is the device. Now let's have a look now at the block diagram. Here is the Hall effect element, and there is some signal processing going on. In particular, there is a amplifier, so probably a chopper type amplifier in order to zero the offset and get a cleaner signal. Then we have this recovery from the probably chopper here, and we have the output. Then we have temperature sensor, because this device, the output is highly sensitive to temperature, and also it may not be linear, so there might be some correction for linearity. And the nice thing about this unit is that it is programmable. You program it through this line here, and you can set the sensitivity of the device as well as the offset voltage as what is zero. And everything is included here in this unit, and it has only a minimal number of pins. So this is the unit, and it is made in with different sensitivities, and say the high sensitivity, we can see it here, to be programmable in the range of 6 to 14 millivolt per Gauss. Okay, so for the 3 Gauss we have said, we're going to get 3 times 10 to 30 millivolt. Okay, so for 1 amp it's going to be fairly low, but for higher current, of course, we are getting a reasonable output. Now the response time of this unit is fairly fast, and we can see here in fact a step response. Let me just get to it. Here it is. It's a step response, and we see here 400 Gauss excitation here, and we see that this is the input of the magnetic field, and this is the output of the device. There's a certain delay, and you see that we are talking about, in this case, 3.6 microsecond rise time, which is kind of nice, but in some application, of course, you like to have it more than that. But let's just keep in mind that this is the device itself, not including say a concentrator, which might slow down quite a bit, depending on the ferromagnetic material used. So now let's talk a little bit about the material that is used for the concentrator, the core material. First of all, we have to realize that all ferromagnetic material do have some hysteresis loop, and there is saturation. So in order to get a high dynamic range, you would like the saturation point to be as high as possible. On the other hand, we don't want the width of the hysteresis to be too wide. We like to be as narrow as possible. Well, for Bmax as high as we can, this is for dynamic range, and the width of the hysteresis has 2 aspects to it. Number one is that it related to losses. The circulation of the hysteresis loop is the energy lost in a cycle, and of course, depending on the frequency, times frequency will be the power loss in the core itself. Now, there's another issue here with the hysteresis, is that if you say there is a current which is bringing the ferromagnetic material to this region and then it goes back, and then you stop the current, this is the remanence value. This is like you've magnetized the element, and this is an error. You'll see a magnetic field, although there is no current passing. And then on the other hand, there's the coercive magnitude of current or field that you need in order to bring the magnetic flux back to zero. So this is an error. This is a zero error. And therefore, you would like to have a unit built with a magnetic material that has this very narrow and this value here as low as possible. I've mentioned earlier that in some cases people have been using laminated cores, and the reason for that is first of all that, or the main reason I should say, that the Bmax of this laminated material used for low frequency transformer, for the same reason, is that the Bmax is 1.5 up to 2 Tesla, which is very high. So you have a high dynamic range. Now you need lamination because these sheets of steel have fairly high conductivity. So if the thickness is high, you have eddy current and there will be high losses, and therefore by having it laminated, the eddy current have a larger resistance, and therefore the losses will be lower. Now, it is possible to use ferrite material or some other ferromagnetic material. Ferrite have only a Bmax of about 400 millitesla, so it's fairly low, and there's actually no much information in the open literature of the hysteresis effect in ferrite in this application. The possibility is that if you do have a problem of hysteresis and remanence here, due to the fact that you expose the sensor to very high current, high field, you can demagnetize it or degauss it by feeding in a current that starts high and then it goes lower and lower and lower. You will find it on maybe a button on a current probes with the Hall effect that are doing that in order to reduce the hysteresis error. That is, then when you work in this area, you will not have this large error. Up to now, I've spoken about the open loop operation. A class by itself is the closed loop operation. Looks similar, but it's different. That is, we still have this ferromagnetic path here. We have the whole element here, Hall effect element. But in this case, we operate closed loop. That is, we sense the magnetic field variation, or DC, magnify it and push it into a winding of opposite direction of the main current. So the objective here is actually to null the magnetic field within this path. This is a better way to go because then you are not dependent on the non-linearities and gain values. You are just looking for the zero. Now once you reach this point of zero, then the n times I here is equal to I here, and therefore the output will be the current of this conductor divided by n, here number of turns, times the resistor. This is used a lot in clamp type probe. In the clamp, the same thing here, only the core here, or this ring here, is split into two, and you slide it, you put the wire in, then you slide it back to get the magnetic path back. Now it's important to note that normally the Hall effect by itself, bandwidth of this loop here, is not very high. It's primarily used for the DC and low frequency. At high frequency, the bandwidth may be not high enough, but if the impedance here is low, then we do have still a transformer, a current transformer between this wire, this winding, it's one turn, and this winding with n turns. And therefore the current here will be n times lower than the current here, and you can measure it the same way. So in the total frequency response of a unit like this, you have at the beginning the Hall effect operation, and then you have a transformer at the higher frequencies when the bandwidth of this amplifier is insufficient. Let me now turn to the invasive sensors. As we have said, an invasive sensor means that you are passing the current through the device. Okay? Here are some nice pictures from Allegro about one device they have, ACS758, and this is the bus bar, you might say, for the current, and inside we have the Hall effect and the electronics. Now here's an exploded view. We see that this is the element, this is the current path, has low, very low resistance, but then we have a magnetic core here above the element, so as to close and to improve. That's a sort of a concentrator, as we have seen before. So everything here is within this unit. This is the device, and this is just the construction around it. So the advantage here that you are very close with the device to the current, but you have to pass the current through the device, and this could be practical up to, say, 200, 300 amp. After that, it will be a little bit difficult to do that. Allegro now came up with a more advanced device. Some other companies are doing similar things, but I'm just showing this as an example. This device is for plus minus 20 amp. It's a small device, and you see they are using these terminals, so they're grouping them. This is for the current part, to have enough cross-section for the copper, for the conductor. Now, this element does not have a magnetic core, but it does have two Hall effect elements put, as I understand, on the both sides of the wire that is passing through the device. And the idea here is that an external magnetic field that will come here will affect these two the same thing, and they'll sort of cancel each other, while the effective or the signal you want to measure is in opposite directions, so that you add the useful signal and you subtract the interference. This unit is a little bit more complex, it's more accurate, it's more sensitive, and again it has all these elements that I've mentioned. It has the temperature sensor and correction, and then you can again you can program it in order to change the sensitivity and the offset, and you get an analog output. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.